Launch serves as the mission's injection point. The actual engineering journey begins once the satellite is released into its target orbit. At this stage, the spacecraft is an inert, tightly folded bundle of uncalibrated hardware, hurtling through a vacuum at 7 kilometers per second. The NASA ISRO Synthetic Aperture Radar Mission, NISAR, is a joint Earth-observing observatory currently facing this operational transition. Its primary objective is the systematic mapping of solid Earth deformation across the entire globe. Secondary goals include tracking the dynamics of the cryosphere and monitoring the health of global ecosystems. The mission lifecycle is structured into 4 macro phases: launch, commissioning, science operations, and finally, decommissioning. Our focus here is the second phase, the intricate 90-day window of commissioning. Failure during these 90 days would transform this multi-billion-dollar international investment into high-speed space debris. This diagram illustrates the dual-agency architecture, integrating NASA and ISRO hardware into a single unified bus. NASA's LSAR system operates on the L-band frequency with a 24-centimeter wavelength. ISRO's SSAR operates on the S-band at a 12-centimeter wavelength, mounted alongside the I-3K spacecraft bus. Managing 2 distinct radar frequencies on one platform requires strict hardware isolation and precisely interleaved operations. The mission utilizes a specific observational mechanism known as the SweepSAR technique. SweepSAR allows the instruments to capture a massive observation swath that exceeds 240 kilometers. This extreme width is necessary to achieve full global coverage on a strict 12-day repeat cycle. This hardware architecture requires a perfectly choreographed activation sequence to ensure the 2 radar systems never interfere with each other. Commissioning cannot begin until the solar arrays have successfully deployed. The spacecraft must also be power positive and locked into a stable Earth-pointing attitude. This Gantt chart outlines the 90-day commissioning blueprint and its 4 distinct subphases. Subphase 1 is a 5-day initial checkout to verify ISRO engineering systems and fire pyros to release launch restraints. Subphase 2 is a 5-day window to safely extend the radar antenna boom and the 12-meter reflector. Subphase 3 is a 6-day spacecraft checkout, focusing on internal avionics and telemetry. During this phase, engineers activate the GPS and begin testing the high-rate Ka-band telecom link. While these checks occur, the satellite must transition into the Reference Science Orbit, or RSO. The RSO is a strict 747-kilometer altitude diamond corridor that is precisely tied to the rotation of the Earth. ISRO calculates and executes necessary orbit-raising maneuvers to reach this diamond between days 25 and 35. Reaching this precise orbital corridor is the physical prerequisite for the radar data to be useful for long-term comparative science. Once the orbit is stabilized, the mission enters a 66-day instrument checkout window. The radars are powered on sequentially, beginning with the radar instrument computer. The digital signal processor is then activated to establish ground truth bit comparisons with pre-launch data. Finally, the transmit and receive modules are powered on in staggered groupings to monitor system performance. This leads to the calibration matrix, requiring 10 distinct types of mathematical calibration before science data can be validated. As this flowchart shows, these calibrations are bound by strict logical interdependencies and cannot happen simultaneously. Initial digital beamforming calibrations must be completed before the system can move into radiometric and geometric parameter checks. Specialized checks, like split-spectrum calibration, are then used to determine corrections for ionospheric electron content. This sequence proves the radars must be systematically taught to interpret the environmental noise they receive. Calibrating the radar requires imaging specific, physically known features on the Earth's surface. The first category of calibration sites consists of homogeneous targets, as seen in these maps of the Amazon and Congo basins. The bare terrain of these basins is used to establish reliable radiometric calibration baselines. The second category consists of point targets. These are arrays of corner reflectors co-located with GPS stations, used for exact geometric calibration. This creates a significant scheduling hurdle. The spacecraft only flies over these targets at exact times. Mission planners use the scatter plot to map overflight windows against the 12-day repeat cycle. This requires interleaving the NASA and ISRO schedules to ensure one instrument remains idle while the other calibrates. Aligning a specific calibration task with a 5-minute flyover window requires very tight operational margins. The intersection of orbital mechanics and fixed ground targets is why a simple power-on sequence takes 66 days to complete. Integrating all these orbital and hardware constraints results in this dense 66-day master schedule. There is one final constraint. ISRO must map in both left-looking and right-looking orientations. A left-looking orientation is required for several months every year to map land ice in Antarctica. The yellow triangles on the timeline indicate points where the entire spacecraft must physically turn around. During a yaw flip maneuver, the entire satellite rotates 180 degrees horizontally in its orbit. Every geometric and radiometric calibration must be repeated from scratch after a yaw flip, as the orientation alters the radar geometry. Maintaining thermal and power stability through these maneuvers requires total synchronization across the satellite's core subsystems. By day 90, all system interfaces are validated, and initial calibration stability is confirmed. The ground data pipelines and science data systems are also fully tested using live radar telemetry. Meeting these criteria officially begins the 3-year primary science operations phase. Eventually, the satellite will reach its final phase, decommissioning. ISRO follows strict debris mitigation guidelines to safely lower the orbit and passivate the craft at the end of its life. This meticulous 90-day blueprint is the precise mechanism that transforms static hardware into a dynamic global observatory.